Implementing Kruskal's algorithm, the union find data structure. One of the most basic graph problems is to find the set of connected components. In Chapter 3, we discussed the linear time algorithms using BFS or DFS for finding the connected components of a graph. In this section, we consider the scenario in which the graph evolves through the addition of ages. That is, the graph has a fixed population of nodes, but it grows over time by having ages appear between certain pairs of nodes. Our goal is to maintain the set of connected components of such a graph throughout this evolution process. When an edge is added to the graph, we don't want to have to recompute the connected components from scratch. Rather, we will develop a data structure that we'll call the union find structure, which will store a representation of the components in a way that supports rapid searching and updating. This is exactly the data structure needed to implement the Kruskal's algorithm efficiently. As each H equals to VW is considered, we need to efficiently find the identities of the connected components containing V and W. If these components are different, then there is no path from V and W, and hence HE should be included. But if the components are the same, then there is a VW path on the edges already included, and so E should be omitted. In the event that E is included, the data structure should also support the efficient merging of the components of V and W into a single new component. The problem: the union find data structure allows us to maintain disjoint sets such as the components of a graph in the following sense. Given a node U, the operation find of U will return the name of the set containing U. This operation can be used to test if two nodes U and V are in the same set by simply checking if find of U equals to find of V. The data structure will also implement an operation union of A, B to take two sets A and B and merge them to a single set. These operations can be used to maintain connected components of an evolving graph G equals to V as ages are added. The sets will be the connected components of a graph. For a node U, the operation find of U will return the name of the component containing U. If we add an edge UV to the graph, then we first test if U and V are already in the same connected component by testing if find of U equals to find of V. If they are not, then union of find of U and find of V can be used to merge the two components into one. It is important to note that the union find data structure can only be used to maintain components of a graph as we add edges. It is not designed to handle the effects of edge deletion, which may result in a single component being split into two. To summarize, the union find data structure will support three operations. Make union find of S. For set S will return a union find data structure on set S where all elements are in separate sets. This corresponds, for example, to the connected components of a graph with no edges. Our goal will be to implement make union find in time big O of n where n is equal to the size of S. For an element U in S, the operation find of U will return the name of the set containing U. Our goal will be to implement find of U in big O of log n time. Some implementations that we discuss will in fact take only big O of one time for this operation. For two sets A and B, the operation union of A, B will change the data structure by merging the sets A and B into a single set. Our goal will be to implement union in big O of log n time. Let's briefly discuss what we mean by the name of a set, for example, as returned by the find operation. There is a fair amount of flexibility in defining the names of the sets. They should simply be consistent in the sense that find of V and find of W should return the same name if V and W belong to the same set, and different names otherwise. In our implementations, we will name each set using one of the elements it contains. A simple data structure for union find. Maybe the simplest possible way to implement a union find data structure is to maintain an array component that contains the name of the set currently containing each element. Let S be a set and assume it has n elements denoted as the set 1 to 3 until n. we will set up an array component of size n where component s is the name of the set containing s. To implement make union find of s, we set up the array and initial it to component s equals to s for all little s in capital S, where little s is an element and capital S is the set. This implementation makes find of v easy. It is a simple lookup and takes only big O of one time. However, union of AB for two sets A and B can take as long as big O of n time, as we have to update the values of component S for all elements in sets A and B. To improve this bound, we will do a few simple optimizations. First, it is useful to explicitly maintain the list of elements in each set, so we don't have to look through the whole array to find the elements that need updating. Further, we save some time by choosing the name for the union to be the name of one of the sets, say set A. This way, we only have to update the values component S for S in B, but not for any S in A. Of course, if set B is large, this idea by itself doesn't help very much. Thus, we add one further optimization. When set B is big, we may want to keep its name and change component S for all S in A instead. More generally, we can maintain an additional array size of length n, where size A is the size of set A, and when a union AB operation is performed, we use the name of the larger set for the union. This way, fewer elements need to have their component values updated. Even with these optimizations, the worst case for a union operation is still big O of n time. This happens if we take the union of two large sets A and B, each containing a constant fraction of all the elements. However, such bad cases for union cannot happen very often, as the resulting set A union B is even bigger. How can we make this statement more precise? Instead of bounding the worst case running time of a single union operation, we can bound the total or average running time of a sequence of k union operations. 4.23. Consider the array implementation of the union find data structure for some set S of size n, where unions keep the name of the larger set. The find operation takes big O of one time, make union find of S takes big O of n time, and any sequence of k union operations takes at most big O of k log k time. Proof: the claims about the make union find and find operations are easy to verify. Now consider a sequence of k union operations. The only part of a union operation that takes more than big O of one time is updating the array component. Instead of bounding the time spent on the union operation, we will bound the total time spent updating component v for an element v throughout the sequence of k operations. Recall that we start the data structure from a state when all n elements are in their own separate sets. A single union operation can consider at most two of these original one-element sets, so after any sequence of k union operations, all but at most 2k elements of S have been completely untouched. Now, consider a particular element V, as V's set is involved in a sequence of union operation. Its size grows. It may be that in some of these unions, the value of component V is updated, and in others, it is not. But our convention is that the union uses the name of the larger set, so in every update to component V, the size of the set containing V at least doubles. The size of V's set starts out at 1, and the maximum possible size it can reach is 2k. Since we argued above that all but at most 2k elements are untouched by union operations. Thus, component V gets updated in at most log base 2 of 2k times. throughout the process. Moreover, at most 2k elements are involved in any union operations at all. So we get about of big O of k log k for the time spent updating component values in a sequence of k union operations. While this bound on the average running time for a sequence of k operations is good enough in many applications, including implementing Kruskal's algorithm, we will try to do better and reduce the worst case time required. We will do this at the expense of raising the time required for the find operation to big O of log n. A better data structure for union find. The data structure for this alternate implementation uses pointers. Each node V and S will be contained in a record with an associated pointer to the name of the set that contains V. As before, we will use the elements of the set S as possible set names, naming each set after one of its elements. For the make union find of S operation, we initialize a record for each element V and S with a pointer that points to itself or is defined as a null pointer to indicate that V is in its own set. Consider a union operation for two sets A and B and assume that the name we used for set A is a node V in A, while set B is named after node U in B. The idea is to have either U or V be the name of the combined set. Assume we select V as the name to indicate that we took the union of the two sets and that the name of the union set is V. We simply update U's pointer to point to V. We do not update the pointers at the other nodes of set B. As a result, for elements W in B other than U, the name of the set they belong to must be computed by following a sequence of pointers, first leading them to the old name U, and then via the pointer from U to the new name V. This pointer-based data structure implements union in big O of one time. All we have to do is to the following sequence of union operations. But a find operation is no longer constant time, as we have to follow a sequence of pointers through a history of old names that the set had in order to get to the current name. How long can a find of U operation take? The number of steps needed is exactly the number of times the set containing node U had to change its name. That is the number of times the component U array positions would have been updated in our previous array representation. This can be as large as big O of n if we are not careful with choosing set names. To reduce the time required for a find operation, we will use the same optimization we used before. Keep the name of the larger set as the name of the union. The sequence of unions that produced the data structure followed this convention. To implement this choice efficiently, we will maintain an additional field with the nodes, the size of the corresponding set. 4.24. Consider the above pointer-based implementation of the union find data structure for some set S of size n, where unions keep the name of the larger set. A union operation takes big O of one time. Make union find of S takes big O of n time, and a find operation takes big O of log n time. Prove the statement about the union and the make union find are easy to verify. The time to evaluate find of V for a node V is the number of times that the set containing node V changes its name during the process. By the convention that the union keeps the name for a larger set, it follows that every time the name of the set containing node V changes, the size of this set at least doubles. Since the set containing V starts at size 1 and is never larger than n, its size can double at most log base 2 of n times, and so there can be at most log base 2 of n time changes. Further improvements. Next, we will briefly discuss a natural optimization in the pointer-based union find data structure that has the effect of speeding up the find operations. Strictly speaking, this improvement will not be necessary for our purposes. In this book, for all the applications of union-find data structures that we consider, the big O of log n time per operation is good enough, in the sense that further improvement in the time for operations would not translate to improvements in the overall running time of the algorithms where you use them. The union-find operations will not be the only computational bottleneck in the running time of these algorithms. To motivate the improved version of the data structure, let us first discuss a bad case for the running time of the point-based union-find data structure. First, we build up a structure where one of the find operations takes about log n time. To do this, we can repeatedly take unions of equal sized sets. Assume V is a node for which the find of V operation takes about log n time. Now we can issue find of V repeatedly, and it takes log n for each such call. Having to follow the same sequence of log n pointers every time for finding the name of the set containing V is quite redundant. After the first request for find V, we already know the name X of the set containing V, and we also know that all other contained in the set X. So in the improved implementation, we will compress the path we followed after every find operation by resetting all pointers along the path to point to the current name of the set. No information is lost by doing this, and it makes subsequent find operations run more quickly. Now consider the runtime of the operations in the resulting implementation. As before, a union operation takes big O of 1 time, and a make union find of S takes big O of n time to set up a data structure for a set of size n. How did the time required for a find of V operation change? Some find operations can still take up to log n time, and for some find operations, we actually increase the time, since after finding the name X of the set containing V, we have to go back through the same path of pointers from V to X and reset each of these pointers to point it to X directly. But this additional work can at most double the time required, and so does not change the fact that a find takes at most big O of log n time. The real gain from compression is in making subsequent calls to find cheaper, and this can be made precise by the same type of argument we used in 4.23, bounding the total time for a sequence of n find operations rather than the worst case time for any one of them. Although we do not go into the details here, a sequence of n find operations employing compression requires an amount of time that is extremely close to linear in n. The actual upper bound is big O of n times alpha of n, where alpha of n is an extremely slow growing function of n called the inverse Ackermann function. In particular, alpha of n is less than or equal to 4 for any value of n that could be encountered in practice. Implementing Kruskal's algorithm. Now we'll use the union-find data structure to implement the Kruskal's algorithm. First, we need to sort the ages by cost. This takes time big O of m log m. Since we have at most one edge between any pair of nodes, we have m which is less than or equal to n squared, and hence this running time is also big O of m log n. After the sorting operation, we use the union-find data structure to maintain the connected components of Vt as edges are added. As each edge E equals to Vw is considered, we compute find of U and find of V and test if they are equal to see if V and W belong to different components. We use union of find of U, find of V to merge the two components if the algorithm decides to include edge E in the tree T. We are doing a total of at most 2m find and n-1 union operations over the course of Kruskal's algorithm. we can use either 4.23 for the array-based implementation of union find or 4.24 for the pointer-based implementation to conclude that this is a total of big O of m log n time. While more efficient implementations of the union find data structure are possible, this would not help the running time of Kruskal's algorithm, which has an unavoidable big O of m log n term due to the initial sorting of the addresses by cost. To sum up, we have the following. 4.25. Kruskal's algorithm can be implemented on a graph with n nodes and m addresses to run in big O of m log n time.